Welcome back, or welcome people who are here for the first time to the Cambridge Research Software Engineering Seminars. This week we've got a local speaker from the University of Cambridge, Gurjeet Jagwani, who is currently working in the Institute of Astronomy as a research software engineer with specific focus on machine learning. Though before that, he did some work at Oxford, also as a research software engineer embedded for radio astronomy. Today, I believe you're going to be telling us about some of your most recent stuff, which is some machine learning pipelines for the project you're on.
Thank you so much for that introduction, Jack. So I'll just be talking about the Cosmos framework that we have developed within Cambridge, and how we are building these huge machine learning pipelines to be reproducible and work at scale. So a bit of context, there's a lot of next generation telescopes that are coming out. Whereas Rubin, which is going to be starting in 2025, the dark energy spectroscopic survey, that has started since 2021. Euclid started observing in 2024. And this is the next generation of data that we are expecting in astronomy, and these are really exciting times. And with these next generation telescopes, we have next generation data rates. So whereas Rubin is expected to observe almost 20 terabytes per day. So that's a lot of data that you need to compute and make sense of. DESI observes like 80 gigabytes, Euclid does 100 gigabytes. So this really sort of, as you can see already, sort of pairs well with machine learning and those sort of algorithms. Focusing more on Vera Rubin, it's going to be one of the biggest surveys we've ever observed. It's going to be 18,000 square degrees, so that's on the sky that it's going to observe. And with 37 billion objects in space and time, that is almost 30 trillion measurements. And the main science goals for this observatory is to understand dark matter and dark energy, take the inventory of the solar system, make a movie of the universe, which is something unprecedented, and also mapping the Milky Way and how the internals of the Milky Way are observed. Most of what our group is interested in is understanding dark matter and dark energy. And to understand those things, we really need to understand how galaxies work. The background image that you see here is the early release from Rubin. You can see there's some beautiful images, many mergers of many galaxies, very nice, pretty spiral galaxies over there on the right. But this is just the beginning of what we're going to be observing with Rubin. And to really understand galaxies, what we have framed our problem as is, let's say there is a distribution of galaxies and their properties. So redshift, the amount of mass within a galaxy, the star formation rate, and whatnot. There is a true galaxy distribution. And what we want to do, and like of all of these properties, what we really want to do is build a model that would slowly but surely learn this true distribution of galaxy properties across the universe. That is the goal of this project. That is the goal of Cosmos. And to tackle this, we have assembled an amazing team. Most of these people here are at Cambridge, 8 out of 12, which I think is great. And yeah, we are developing these algorithms to answer this question. So how do we answer this question? Like, what is the galaxy property? Like the distribution of galaxy properties that we see in the universe. So a way to answer this question is through a forward model. So what we do is we have a population distribution, a random population distribution of many galaxy properties. we just randomly draw something from that distribution, let's say a Gaussian, and then we turn it into an observable. So something that we would observe from our telescopes, something like the flux of a particular object. We're talking about galaxies here, so flux of a galaxy. And then we add some sort of realism to it, like what does it really look when we actually look at the telescope? And that would give us a forward model from going from this distribution of galaxy properties to what we would observe through a telescope. And to do this, we use diffusion models, where we have a simple base density that sort of transforms into the population distribution that we're interested in. And then the intrinsic properties of those distributions are then converted into observable features that you would mean to see from a telescope. Those are then converted into mock observations, so adding noise and making selection cuts that you would actually see in a catalog line that you would observe from telescope. And then you compare that to real data and see how well your fit is and how well your main population distribution shows your catalog or represents the catalog. So a very important part of this is the physical model. So if I go back again, the physical model is here, where you have the intrinsic properties from your population distribution and you want to convert them into something you see from telescope. So this has been worked on by many talented people before, showcased in the 2020 that we released. This is a neural emulator of generating either spectroscopic result or a photometric result, and within the 16 parameter stellar population synthesis model. The stellar population synthesis model here, for people who are not familiar, is basically different parameters and different galaxy properties that we can characterize within this. So you have 16 different of these properties, like the age of that galaxy, the redshift, so how far is that galaxy, how many stars do we expect to see, is it still star forming, is it not? These are all the parameters that we're interested in. And then with those parameters, we emulate a spectra or a photometric. So we then train a neural network to show, okay, looking at these different parameters, what kind of spectrum should we observe? Or looking at these different parameters, what kind of fluxes should we observe? There is the original SPS code or FSPS code, which does it already, but it's quite slow for our methods. So we made these emulators to get almost 10,000 times speedups. And the good thing about them is they are as accurate, so sub% accuracy as the original FSPS code, and they're also fully differentiable. So what kind of real data do we calibrate our population model on? We calibrated on the Cosmos 2020 catalog, which is 26 different bands. So 26 different photometric bands, wavelengths, and observed around 400,000 galaxies. And we take those 400,000 galaxies, observed in these 26 bands, and we calibrate our model based on that. So the next question is, what should the data itself look like? So if I go back again and show this flowchart, we go from some random distribution, we put in our emulator, we get some observable features, and then what we want to do now is add noise and selection cuts. So normally when you observe from a telescope, it's not going to be a perfect observation of the galaxy. There's going to be some noise. There's going to be some sort of selection effects that are happening. How do we incorporate that into the model? We develop another diffusion model for this, which is a non-parametric diffusion model that captures this distribution of errors and noise very well. So on the left, on the y-axis, you see the noise, and on the x-axis is your flux magnitude. So for each flux magnitude in different photometric bands, what is the noise that we observe? And it's not a simple distribution like Gaussian, like some of these are very multimodal. So we had to use something like a diffusion model to capture these distributions. And then we compare those noisy fluxes and compare them directly to the catalog that we observe in the universe. So how well do these different colors or different photometric bands at different wavelengths show? So how well our population model produces these galaxies in these different photometric bands. And as you can see, it works pretty well. So our work in Pop Cosmos, that is pretty good and very well calibrated to the original data that you should expect to see from the Cosmos 2020 catalog. This is the full model calibration loop. So basically, you go from this population model that we have, which is the SPS parameters, the 16 SPS parameters, again, different parameters like mass, flux, star formation rate, what's the redshift of each galaxy, etc. And then we throw that into an emulator and we get noiseless magnitudes. So just fluxes that we don't have any noise into. Then we apply the data model onto them and get noisy fluxes that look like what you would actually observe. And then we compare those noisy fluxes to what you would see in the catalog. And we train our diffusion model on that, and slowly but surely, you match the real data and you get pretty good results. So what can we do with this? We can also forward model other surveys. So we can take the same SPS parameters that we have, throw them into the emulator, get the noiseless fluxes, but with different surveys, you have different noise models, you have different selection cuts, and we can make those again, and we can forward model these other catalogs like LSST that's coming up, kids, gamma. What it gives you at the end is a learned population level distribution on all the galaxy properties that you would see in a catalog. So these are the 12, not the 16, but the 12 galaxy properties that you would observe. And this is the distribution that we get at the end from all of these. So it's redshift here, the AGN, how much AGN does contribute into a galaxy, active galactic nuclei, and other properties that we are interested in. What you can do with this now is use it as a prior for downstream inference of individual galaxies. So you have a population level prior, which tells you this is what we would observe for all of these many galaxies, around 400,000 galaxies. What is the property for this particular galaxy that we want to find out? So we do an MCMC analysis and we almost get 15 GPU seconds per galaxy under the Pop Cosmos prior. There is another prospector prior that we use as well, which is the one here in blue, that takes 0.6 GPU seconds. We enable this by using affine, which is our MCMC sampler. It's an affine invariant MCMC sampler that we have shown to be really scalable and works with as many galaxies, as many data. Like it shows very good, strong scaling with more data. Underneath all of this, to enable all these diffusion modeling and all of these different estimates and things that we're doing, we have flowfusion, which is our generative modeling and density estimation engine. It has 3 different types of machine learning algorithms in there, which are generative modeling algorithms. So going from noise to data, score-based diffusion models use SDEs, flow matching uses a linear interpolation path, and symplectic flows use something called a volume preserving path. Most of our work is very reproducible, so we make our trained models in code to use them for downstream tasks available in the PopCosmos public repository, along with demo notebooks that reproduce plots from the papers using the trained models. We ensure that most of our code is well documented within the repositories so that everybody can use our tools. And additionally, we make all of our data products available on Zenodo. Final remarks and some future work that we're doing now is we are trying to infer other surveys. So the kilodegree survey, which is around 70 million galaxies, what we want to find out is what are the SPS parameters for a given galaxy in all of these different surveys. And we have already processed 4 million galaxies, and we get around 6.5 GPU seconds, which is almost half than what we had before doing the Bayesian inference on these galaxies. One other thing I would like to point out is the inference of these algorithms is quite slow, like in terms of if you want to scale it up to 70 million galaxies, this is not really scalable right now. But we are developing new tools. So the symplectic flow right here sort of tackles that, where our main bottleneck is the divergence that you have from the noise distribution to the data distribution. And if you have a volume preserving path, there is no divergence. So you can basically have really fast inferences. There are some caveats to this. We get not an exact likelihood, but we get lower bound estimates. But it's still almost 30 times faster. And speaking a bit more about this, our pipeline right now is calibrated on a selection cut here that you see, which is the magnitude limit of the IRAC 26 channel, which is this one, IRAC 1 channel. So we cut this selection of the catalog because we think that is the most complete, that is the catalog that we trust. Any sort of measurements after that, we don't really trust them as much. So the catalog is more complete, as the astronomers would say. And we make that cut there with our data model within it. We are also working on scaling this up a bit more. So we can do amortized neural posterior estimation, which is ANPE, which basically takes rather than doing an MCMC sample at the end, because you have a forward model, you can learn what the posterior should look like for each data point in reverse. And we are currently in the process of training that and making that work very soon. and we are expecting around 50 times speed up with just that. We are also developing something called STAT. This is a machine learning algorithm directly focusing the likelihood evaluations on diffusion models. So again, the main bottleneck with these algorithms is the divergence computation, but we have figured out a way to amortize this computation where you can just learn the divergence with a small neural net, and you can infer the divergence at every single point that the diffusion model takes, and get a very good likelihood at the end. But this is still under works, so there will be more on that. And in terms of doing better on the reproducibility, we are now in works with developing better. We are looking to develop the Pop Cosmos pipeline even deeper. So we're going to be using the JWST data coming in and making the. So right now the Pop Cosmos pipeline works up on redshift 6, and with JWST coming in, we can, I think, go up to like 8 or 10, and that would be a much deeper cut, and that would give us better constraints on these parameters. And once we have this new training loop, we want to release the full training loop to everybody else so that people can recreate our pipelines and recreate the whole machine learning model from scratch. And yeah, that's it.
Thank you, Gurjeet, for such an interesting talk. If people have questions, please do put your hand up in the room or online. Either put your hand up or dump it in the chat. You did. I guess I would start with a question, which is, having done this stuff, is there anything sort of, has it mostly confirmed what people previously thought about kind of distribution of properties? Or have there been any surprising results?
There have been many surprising results, which I am actually less informed about, but I think the star formation rate density especially was very different than what we expected to be. And a recent paper has been released by one of our colleagues. I can just quickly show him. Sinan, who works at the IOA here, has released this new paper, and they show by using this model that there are much different, like galaxies evolve in a very different way than how we thought they would.
Yeah, correct.
What has, as a research software engineer, what has your contribution been like in comparison to, say, other members of the team? Like, what have you been working on? Some aspect of the pipeline, or
so most of my contribution has been in developing flowfusion, where I've most of these algorithms with help from the other researchers as well. Especially the symplectic flows and the flow matching, developing that. Other than that, I also developed the data model for calibrating all of Pop Cosmos, and getting the diffusion model working for that. I've also been working on the affine, the MCMC sampler, improving the sampling speed, so that before we had 15 GPU seconds per galaxy, and now we have like 6.5, which is almost 2 times speed up, which came from affine. And also the release of Pop Cosmos, which I helped create as well.
Thanks.
Any more questions?
Where does all this compute run? Like, where is it? Is it happening in the university? Is it happening in the cloud?
This is all on clusters on CST3 or on there's some compute in Stockholm that the group has. Yeah.
Is it sufficiently expensive that you can't rerun it from scratch to find out how reproducible it is?
So the full course training loop right now takes around like 2 or 3 days. So it's not that bad. You could probably run it again.
2 or 3 days on
On
How
an
many?
A100.
what?
On one A100.
Oh,
Yeah. Yeah, it's not that bad. But I think we are, so then one of the next challenges that we have now is to add to these 16 parameters that we have and add an image parameter, so for modeling images directly. That is not going to be trivial, and that would need a lot more compute. Yeah.
Any questions online?
Yes, it's also.
I don't see anyone with that. Why do you not see? No, in which case, I will say thank you very much for being interested. It's interesting to hear about some of the other research software that's going on throughout the university.
Yeah.
But if you can just join me one more time in thanking Gurjeet for today's talk.